infectious diseases, research, medicine, health. Welcome to Outbreak News Interviews. And now, broadcasting from the Outbreak News Skylar Studios in beautiful West Central Florida, here is your host, microbiologist and editor of OutbreakNewsToday.com, Robert Harriman.
Well, hey everybody, this is Robert, and welcome to Outbreak News Interviews. Now, according to the World Malaria Report, there were 219 million cases of malaria globally in 2017. And this resulted in 435,000 fatalities. Now, drug resistance poses one of the greatest threats to malaria control and results in increased malaria morbidity and mortality. But now, Vanderbilt biomedical engineers have discovered a way to rapidly detect critical information about malaria drug resistance almost instantly from a patient's single drop of blood. So joining me today to discuss this quick DNA test is Mindy Leelawong, PhD. Dr. Leelawong is a research assistant professor of biomedical engineering at Vanderbilt University. Dr. Leelawong, welcome, ma'am, to the show.
Thank you for having me.
You bet. Well, let's just go over a little bit of primer, a little bit of basics on malaria before we get started on your research. What is malaria? How serious can it be? And how common is it?
Sure. So malaria is a disease that's caused by a parasite, and these parasites infect red blood cells. They're transmitted by the bite of mosquitoes, and there are several species that cause malaria, but the one that I study, Plasmodium falciparum, accounts for the vast majority of the cases and deaths. And so when a person is infected with malaria, their initial symptoms are sort of flu-like, so fever, chills, muscle aches, fatigue, nausea. But when you have to be concerned is when it becomes severe, and that includes anemia, problems with blood coagulation, organ failure, and cerebral malaria is a specific concern because that is characterized by coma and seizures.
And how common is malaria worldwide? I kind of gave the numbers, but I mean, where do we see it at mostly?
Yeah, so 219 million cases is a lot of cases. And the vast majority, over 90% of those cases, occur in Africa. And then about 5% of those are in Southeast Asia. So usually tropical areas of the world, places where you do see a lot of mosquitoes.
Now, the emergence of malaria drug resistance just further compounds an already difficult public health situation. What is the current situation concerning drug resistance? Right.
So the current first-line therapy treatment for malaria is an artemisinin-based drug. So artemisinin is a very potent drug. Just in 2015, the Nobel Prize, part of it was awarded to the person who discovered it. And it is partnered with a combination drug, so it's given in the form of a combination therapy, and it's highly effective. But in Southeast Asia, just in this past decade or so, we've seen the emergence and spread of parasites that are resistant to artemisinin. So as a consequence, there's been an acceleration of elimination efforts in Southeast Asia, and they've actually seen a significant decline in the number of cases there. But I want to point out that it's really important to preserve this drug because it is so potent. And so it's really necessary to keep a very close watch on this and to prevent the further spread of drug-resistant parasites.
Now, this resistance that you're talking about in Southeast Asia, this is on the Thailand-Cambodia border. Am I correct?
Yeah.
Are we seeing that anywhere else?
Vietnam, it's mostly within Southeast Asia. So Laos, Vietnam, Thailand, Myanmar. Yeah.
Okay, so how would somebody typically determine whether a drug will work against a malaria strain?
Yeah, this is a very difficult thing to look at. So it's a complicated process, and usually there are two ways to look at it. One is to administer the drug and then look at blood smears from those people receiving the drug and monitor it over a course of a few days to determine how much parasite reduction is seen. Another way to do this is to take parasites from an individual who's infected, culture them, apply the drug, and then monitor parasite reduction. So both of these are very complicated ways to monitor it, but it's really the best way to do it. But there are some molecular markers for artemisinin resistance. Those are usually identified through sequencing because there are a few different mutations that are associated with it. And we're still in the early stages of identifying and characterizing these mutations.
And then that really brings me to the work that you've been doing and your colleagues. You came up with this quick test, essentially, that actually eliminates some of the steps that you would find in a normal DNA type test. Can you talk about that?
Yeah, sure. So the most sensitive tool that we have for diagnostics is PCR, or polymerase chain reaction. And it's this process, this enzymatic process, that allows us to copy DNA to a level that's high enough for measurement. And this is usually done with some dyes. And those dyes are monitored over the course of about an hour during this enzymatic process. And so it's very sensitive, but it requires some very precise conditions. And so because of that, usually what happens, especially with blood, is that you have to go through this long purification process. That's mostly to remove some inhibitors to this process of PCR. And so this step of extracting DNA from the sample is really laborious. It takes maybe 40 minutes if you have one sample, but a couple hours if you have a few samples. It requires centrifugation and heat blocks. So practically speaking, it's just not possible to perform in rural settings. But if you can't perform it, then you can't perform PCR. And so what I wanted to do was to eliminate this bottleneck by removing this step of DNA extraction and be able to put blood directly into the PCR reaction. There were a couple of different things that I had to do in order to make this possible. One was to use an enzyme that was engineered to be more tolerant of the contaminants that are found in blood. But really the enabling feature was to use these dyes that are not commonly used with PCR. And so these dyes are more optically compatible with blood, and they bypass the optical interference with blood. So usually the dyes are within this absorption spectra of blood, and they just can't be seen because of that. And so I used dyes that had longer wavelength that could bypass that interference.
Now, there's several benefits to this technique that you developed, and you kind of mentioned probably the main one, the ability to use it in a rural environment, to use it in the field, basically. That is the main benefit, unless you disagree with me.
No,
I
agree.
Are there other public health benefits that go along with this?
Yeah, so that is a main benefit. And I just want to point out that usually what happens is if you want to use this very sensitive test, but you're in a rural setting, what happens is that you get dried blood spots. So you put the blood on a special type of paper, then you ship that paper to your central laboratory and store it until you're ready for processing. So that does add a lot of time to this process. And it's just not feasible. So if you are in a rural setting where it's not possible to have communication back and forth between the healthcare worker and the patient, then you're really going to be losing out on being able to communicate this information to your patient.
Well, it's a very interesting technique, and there's potentially a lot more applications to this. Dr. Leelawong, what else are you looking to do with this technique?
So I should point out that this was designed sort of as a proof of principle. And so initially when I did this, I looked at a mutation that's associated with chloroquine resistance. So this is a key mutation. It's a single mutation. And what I would like to do now is to adapt this for artemisinin resistance. And in that case, there are several different mutations that are associated with artemisinin resistance. So it'll be a little bit more tricky, but what I would like to do is to develop this assay so that we can assess multiple mutations simultaneously. But yes, absolutely, this work can be applied to other pathogens, especially those found in blood. So, for example, you can think of HIV, trypanosoma parasites, hepatitis C, for example.
Yeah, that's great. Good stuff. Any final thoughts on malaria, your research, or anything else?
Yeah, I would like to say that I've really enjoyed talking about this work recently, and I'm optimistic that this research will provide more tools for other scientists. But also I hope that this work can raise some awareness for the disease as well. Because to put it in perspective, a child dies every 2 minutes from malaria. So this is a disease that disproportionately affects poorer and more unstable regions of the world. And I hope that we can all learn a little bit about malaria and its effects on other people.
Well said. And for those that are interested, I'll link to the paper in the show notes page when I publish the podcast. And I want to thank you, Dr. Mindy Leelawong, for your time and your expertise, and congratulations.
Thank you very much. Thank you for having me on your podcast.
You bet.